So we will be talking about Arithmetic and Logic Unit, or ALU. So what we have here is a diagram of an ALU. This is a very useful device which appears in all computers and microprocessors. It's sort of a heart on how you do calculations and logic operations. Here is the function of the ALU. In general, we'll have any number of functions. We've chosen operations, so we will have operations, which is like a multiplexer select 2 down to 0. And depending upon what this ALU select is, we'll have a different function. Next, we have two inputs, nibble 1 and nibble 2, each 4-bit in this example, and output result. So if the operation selected is 0, then it performs an addition, which adds nibble 1 and nibble 2. If the operation select is 1, it tests if nibble 2 is greater than nibble 1. If so, it performs a subtraction, which then set the flag to 1. So you can pick any kinds of functions that you want here. The ALU select will select different operations. We can also have logic operations. When ALU select is 2, then we'll have a bitwise AND. Each bit of nibble 1 gets added with nibble 2. If the operation select is 3, then we'll have bitwise OR. Each bit of nibble 1 gets ORed with nibble 2. If we have 4, then it will perform a bitwise XOR. Each bit of nibble 1 gets XORed with nibble 2. Next, if the operation select is 5, then it will perform a bitwise inverse of nibble 1. Each bit of nibble 1 gets inverted. Next, if the operation select is 6, then we'll have a bitwise inverse of nibble 2. Each bit of nibble 2 gets inverted. And finally, if operation select is 7, then it performs an addition of nibble 1 plus nibble 2 plus 1. In addition, we bring out two lines, which corresponds to a carry-out flag and a sign flag. The negative flag will get set to 1 if the most significant bit of the result is the output of the 2's complement negative number. So these negative flags and carry-out flags are useful for doing branching instructions in microprocessors. So the ALU then is a general operation for doing arithmetic and logic operations. Next, we will be discussing about the ALU in VHDL. So to implement the 4-bit ALU, we have here the VHDL program. We have nibble 1, nibble 2, 4 bits, 3 down to 0. We also have the operation, which is 3 bits, 2 down to 0, and the carryout flag and sign flag. The output result would be 4 bits, 3 down to 0. So we have here the architecture of the ALU with a 5-bit temp that is used for addition and subtraction. And next we have the process with nibble 1, nibble 2, operation and temp in the sensitivity list. Then we initialize the flag to 0. Next we have the case statement, operation. When operation select is 0, we want to add nibble 1 and nibble 2. But we also concatenated 0 with the ampersand to nibble 1 to make them 5 bits. Then added them together with a plus sign, so that would be nibble 1 plus nibble 2. The most significant bit of the temp would be the carryout flag, and the lower bits, which are the 3 down to 0 bits, will be the result. So when operation select is 1, we want to test if nibble 2 is greater than nibble 1. So we will have nibble 1 is greater than or equal to nibble 2. The minuend would be the nibble 1, and the subtrahend would be the nibble 2. The flag will be cleared. Else, it will have the minuend as nibble 2, and nibble 1 would be the subtrahend, but with the flag set. So next, when operation select is 2, then it will perform a bitwise AND. Each bit of nibble 1 gets ANDed with nibble 2. When operation select is 3, then it will perform a bitwise OR. Each bit of nibble 1 gets ORed with nibble 2. When operation select is 4, then nibble 1 gets XORed with nibble 2. When operation select is 5, nibble 1 gets inverted. Then when operation select is 6, then the nibble 2 gets inverted. When others, then we want to add nibble 1, nibble 2, and 1, with the most significant bit at the flag and the lower bits at the result. So that's the end of the case, process, and architecture. Next, we will have the simulation of the VHDL. So for the simulation, we need to compile VHDL file that we created. So just click the start compilation and we wait for the dialog box to appear. So the dialog box appeared. Just click OK, then go to File, click New, and select Vector Waveform File. So the next step for us is to edit the grid size and the end time. So click Edit, go to End Time, then put 16 microseconds, click OK, then go to Edit again, select Grid Size, and make sure that the period is 1 microsecond. Next is click in this space, right click, and select Zoom Fit in Window. So there you have it. Next is to insert the nodes initialized in VHDL file. So right click in this space, insert node or bus, then click Node Finder, select List, make sure that the filter is Pins All, then highlight everything. Then copy to select the node list and just click OK. After that, we will have this kind of look. Don't worry about the axis, it's not yet. That means that is the output. The ones that has no X is the input. So let's arrange it so that the input is on the upper part. Next is to select or to load values in the input. So just right click on the operation and select value, count value, and make sure that the timing is 1. So just click OK. Next is the nibble 2. Have its value as count value also, but its timing should be in 2 microseconds. Next is nibble 2, right click, value, then count value, and timing should be 1 microsecond. So simulate or to compile, first we need to start compilation. Yeah. So we'll just need to wait for the dialog box to appear. So as you can see, a dialog box appeared, so just click OK. So next, to start the simulator, just click this button. And there you have it. We have the simulation. So we'll check if the result is correct. So when the operation select is 0, then it will perform an addition of nibble 1 and nibble 2. In this case, nibble 1 is 0, nibble 2 is 0, so the sum would be 0. In operation, so as you can see, if the operation select is 1, then it will perform a test if nibble 2 is greater than nibble 1. In this case, nibble 2 is greater than nibble 1, so the nibble 2 will be the minuend and nibble 1 would be the subtrahend. The sign flag is set. So if the operation select is 2, it will perform a bitwise AND. Nibble 1 ANDed with nibble 2. So 1 ANDed with 2, the result will be 0. So if the operation selected is 3, then it will perform a bitwise OR. 1 ORed with 3, then that will be 3. Next, when operation select is 4, it will perform a bitwise XOR. Nibble 2 XORed with nibble 1, or nibble 1 XORed with nibble 2. So that would be 2 XORed with 4, then that would be 6. So if the operation select is 5, it will perform a logic operation of bitwise inverse of nibble 1. So we have nibble 1 equal to 2, and the inverted value of that would be 1101. So next, if the operation selected is 6, the logic operation performed would be the bitwise inverse of nibble 2. Nibble 2 has a value of 0110, which is equal to 6. So the inverse of that would be 1001, which is equal to 9. Lastly, when operation select is 7, it will perform a function of nibble 1 plus nibble 2 plus 1. So nibble 1 has a value of 3, and nibble 2 has a value of 7. So that will be 3 plus 7 is 10. Then added with 1, so that will be 11. Based on the results, we can conclude that the ALU operations are in fact correct.